Welcome back. We're going to go to the third topic of oligosaccharides, common disaccharides. And the first disaccharides we'll talk about is sucrose. So, what is disaccharides? Disaccharides are the simplest form of oligosaccharides. It's only composed of two monosaccharides units. It's naturally occurring, highly abundant in nature. However, some of the disaccharides is produced from the incomplete hydrolysis of higher oligosaccharides or polysaccharides. For example, maltose is the product of starch digestion. Most disaccharides are water soluble with a certain level of sweet taste, and the most common found disaccharides are sucrose, lactose, maltose, and trehalose. Sucrose is a stereotypical type of sugar extracted from sugarcane and beets. Monosaccharides units are glucose and fructose. Lactose is a type of sugar extracted from the milk. Composing monosaccharides units are glucose and galactose. For maltose, this is a type of disaccharides formed from the hydrolysis of starches. It's made of glucose and glucose. Trehalose is extracted from the bacteria and the plants. It's composed of two glucose units. The linkage between these glucose units is alpha 1,1 glycosidic linkage. So, as the main product of photosynthesis, sucrose is actually ubiquitous in all types of plants. It's especially high abundant in sugarcane and beets, as well as other common types of fruits, and is commonly known as table sugar. So the sucrose structure is a disaccharides. It's made of one glucose unit and one fructose unit. The linkage between these monosaccharides is beta 1,2 glycosidic linkage. So this is a head-to-head linkage that is quite unstable, and it's pretty easy to be hydrolyzed under acidic condition or with the assistance of enzyme. For example, the inverted sugar is a stereotypical example of sucrose hydrolysis. Sucrose is actually a non-reducing sugar, so there's no reducing end in sucrose. However, the sucrose can be hydrolyzed into glucose and fructose under heat. So the hydrolyzed sugars, glucose and fructose, they're reducing sugar. They can react with protein to go through Maillard reaction. Also, the sucrose can break up into fructose and glucose units, and then they will be transformed into aromatic molecules. This is called caramelization reaction. There's no protein involved in this reaction. Please type the answer for the quizzes in the discussion forum. One of the most important sucrose hydrolysis product is inverted sugar. So if sucrose is always readily hydrolyzed, and in the industry, the mixture of the hydrolyzed product, fructose and glucose mixture, is known as inverted sugar. Sucrose is hydrolyzed through heating with the assistance of enzyme and acid. Here we have a short video demonstrating how the inverted sugar is made. To measure the concentration of inverted sugar, it's usually done by an equipment called polarimeter. It measures how much light can be rotated by the sugar. The sucrose rotates the light towards the right by 66.5 degree, where the inverted sugar rotates the light to the left by 39 degree. And the 39 degree to the left is calculated based on the individual component of the inverted sugar, glucose and fructose. For the glucose, the light is rotated to the right by 52.7 degree, and for the fructose, the light is rotated to the left by 92 degree. Plus them together, and we get the light rotation of inverted sugar by negative 39 degree. Here we have a short demo.
This is a solution of sucrose. It's a chiral molecule and it's dextrorotatory, i.e. it rotates plane polarized light to the right, so it's now able to pass through the second filter. Other sugars, like glucose and fructose, are chiral too. Glucose rotates light to the right, hence also being known as dextrose. Fructose, which is sold in supermarkets as fruit sugar, rotates light strongly to the left, and is also lesser known as levulose. But have I just added a glucose solution or a fructose solution? Both look the same. However, if you turn one of the filters back and forth, you can see our solutions are rotating in opposite directions. The one on your left is fructose. Now here's a cool extension. This solution here started off exactly the same as the sucrose solution on your right. I added a few drops of lemon juice and then boiled gently for about 5 minutes. Sucrose is a disaccharide of glucose and fructose. What I've done is to begin hydrolyzing it. We now have a mixture of sucrose rotating right, glucose rotating right, and fructose which rotates strongly left. Watch as I rotate. The solution in the center now rotates somewhere between the other two. Left hydrolyzing long enough, the solution will begin to rotate left, hence being known as invert sugar syrup.
The physical property of inverted sugar is slightly different from the sucrose. For example, it's a sweeter, low water activity, longer shelf life, less prone to crystallization, and it's more hygroscopic. All these physical properties allow inverted sugar to be priced higher than the sucrose in the food industry. The enzymes that are involved in the enzymatic hydrolysis of sucrose are sucrase and invertase. These enzymes act at different sites. So for sucrase, it targets at the glucose side. So as shown in the demo, the sucrase cleave the bond closer to the glucose. Invertase targets at fructose side. So as shown in the demo, the invertase cleave the bond closer to the fructose. These are the quiz questions. Please type in the answer and we'll discuss them during the next lecture.
Ever stop to wonder what makes that morning cup of coffee or that favorite dessert of yours so delightfully sweet? The answer is likely to be a common sweetener that we use every day, sucrose, also known as table sugar. Sucrose is a disaccharide, which is the simplest form of oligosaccharides. This means it's composed of just two monosaccharide units. In the case of sucrose, these units are glucose and fructose, connected via a beta 1,2 glycosidic linkage. This unique structure is often referred to as a head-to-head linkage. However, it's worth noting that this linkage is unstable due to high strain, making it easily hydrolyzed or broken down. This is why sucrose is classified as a non-reducing sugar. Sucrose is highly abundant in nature. It's the main product of photosynthesis, which makes it ubiquitous in all plants. You'll find it in high abundance in sugarcane and beet, as well as fruits. Sucrose is usually the standard of sweetness for other sweeteners. Now let's delve into something a little more complex: inverted sugar. When sucrose is hydrolyzed, it can produce a mixture of glucose and fructose, known as inverted sugar. This can be achieved by simply heating an aqueous solution of sucrose. In the industry, an enzyme such as sucrase or invertase, or an acid like lemon juice or cream of tartar, is added to facilitate the reaction. The concentration of the product can be measured by a polarimeter due to the inversion of optical rotation. Interestingly, inverted sugar is of higher sweetness, more hygroscopic and less prone to crystallization compared to sucrose. That's why it's preferred in bakery. Even though both sucrase and invertase can hydrolyze sucrose, they target different sites of reaction. Sucrase, an aglucosidase, targets the glucose side of the glucosidic linkage. On the other hand, invertase, a B-fructofuranosidase, targets the fructose side. In summary, sucrose, our everyday sweetener, is a disaccharide made of glucose and fructose. It's highly abundant in nature, being the main product of photosynthesis. It can be easily hydrolyzed to produce inverted sugar, which is of higher sweetness and is favored in the baking industry. The enzymes sucrase and invertase facilitate this hydrolysis, each targeting a different side of the glucosidic linkage. So next time you enjoy something sweet, remember the fascinating science behind that sweetness.